All right, everybody, we're going to go through 5 problems together here off of our 12-1 worksheet. The first set of problems is asking you to determine if line AB, should really be segment AB, is tangent to that particular circle or not. And the main idea at work in these problems right here is the very first theorem that we talked about in our video notes on section 12-1. And that theorem said that, let me have this in front of me right here, it basically said that if, I'm trying to get the wording just right here, it basically said here that if a line is tangent to a circle, then that line needs to be perpendicular to a radius that's drawn to that point of tangency. So the real question is this angle right over here, angle BA, and there's not another point over here, so let me call this angle BAC. So if this angle right here between line segment AC and line segment AB is a right angle, then we know that we have a tangent line. And if it's not a right angle, then we know that it's not. So the key here is triangle ABC, this big one here. And we've got line segment AB with a length of 6.6, BC, which appears to be the long side, with a length of 9.2, and then AC down here on the bottom. Now, an important thing to understand is that a point in the middle of a circle can be assumed to be the center of that circle, so this point right here. That means that this line segment coming from that point, let me call that point D, to A, has a length of 4.4. That would be a radius of the circle then. Well, then DC would be a radius as well, and it would have the same length of 4.4, which would make the entire bottom side of this circle, line segment AC, 8.8. So now what I've got to do is compare this side, and this side to find out if these 3 sides will actually form a right triangle or not. So we'll check the Pythagorean theorem. C squared is equal to a squared plus b squared. And unlike some work that we did back in chapter 8, we don't really care if this triangle is acute or obtuse. We just want to know if it's right or not. So C would be the longest side, which would be the 9.2, and that would go here. The A and the B then can be used interchangeably, although normally we would let A be the smaller side, which would be 6.6. and we'll square that, and B would be the intermediate side, which would be 8.8 quantity squared. So let's go to our calculators now and see what happens when we try this. Okay, I gotta fire this guy back up here, and what have I learned? That's probably a little bit easier to see. Okay, so our long side here was 9.2, so let's see what happens when we square that. So 9.2 is going to get squared to give us 84.64 for this left side. 84.64 equals, and I got a feeling this right side is going to be too big. We can put all of this into the calculator at once, guys. 6.6 squared and 4.4 squared. So 6.6 squared plus a 4.4 squared is going to get us a total there. I think I did that wrong. 6.6, 8.8, excuse me. Did that, there we go, 6.6 squared plus an 8.8 squared, there we go, and we end up with 121 on the nose there on the right hand side. So what we can see right away is that C squared here is not equal to a squared plus b squared. That means that angle BAC, this angle right here, is not a right angle. Therefore, line segment AB is not tangent to the circle, and that's where this answer came from. Now, if we ended up with a nice statement here, like 121 equals 121, then we would have a right angle, and therefore the line would be tangent to the circle, but that didn't happen here, so that's why number 1 was not tangent. 2, 3, and 4 work in a similar manner. Let's jump to number 5. This one works the opposite direction here. In this case here, they're telling you, assume that lines which appear to be tangent are tangent. They're letting you make the assumption here. So that means that we've got a line segment up here on the top of this figure that is tangent to this diameter coming across. The reason we know that's a diameter is because of this dot right here in the middle, which we are allowed to assume is the circle. So if we know that we have a tangent, we know that this angle right here must be a right angle. So the big idea to take across from this theorem here, guys, at the beginning of chapter 12, is that a tangent line is always perpendicular to the radius drawn to that point of tangency right there. So we know that we have a right triangle, and that's how we're going to figure out this missing side, which I'm going to call x. So, since we know it's a right triangle, we know the Pythagorean theorem works. We know that leg squared plus leg squared has to equal hypotenuse squared, so let's fill in what we know. We're missing one of our legs, that's x. The other leg is 10, and the hypotenuse here is 14.5. So let's see what we've got. X squared plus 10 squared is 100, and that 14.5, we're going to need some help squaring that, I think. So 14.5 squared is going to get us 210.25. So that goes right here. Okay, 2 steps and we got it, guys. First thing we're going to do, we're going to subtract the 100 from both sides. Okay, and that is going to get us x squared, those cancel, is equal to, that's going to be a 110.25. And to undo the square on the x, we'll do a square root on both sides. And let's see what happens. Looks like this is going to be a little bit bigger than 10, but smaller than 11. So how did I get that? I took the 210.25 minus 100 to get the 110.25, and now we want to take the square root of that last answer, and that gets us, oh, nice clean answer of 10.5 here for the value of x. Okay, so that is our answer there. Yep, it works out. And that's how 6, 7, and 8 are going to work as well. Okay, let's jump to number 9. This is an interesting problem. And usually people struggle with these a little bit at first because they don't quite see how it connects. But then once we do one, people tend to go, oh, yeah, that's it, and realize that it's not too bad. The big idea at work in these problems right here is theorem 12.3. And in our notes, this is what I call the ice cream cone theorem. 12.3 says that when you have a circle looking something like this and an exterior point out here, there are 2 tangent segments that you can draw to the circle from that one exterior point. So one of them might look something like this. The other one might look something like this. And the ice cream cone theorem tells us that those 2 tangent segments have to be congruent to each other. And that is really the idea that's at work within this problem right over here. All right, so we're supposed to find the perimeter of the polygon. The polygon here is the triangle going around the outside of the figure. And you can see right away that we know 2 of the 3 sides. This left side in the figure is 23.7. This bottom side is 23.5. So when I go to actually find the perimeter, we're going to take those 2 sides and add them together. But we also need the length of the third side, this one right over here, which is unknown. So let's talk about how we're going to find that. The one other interesting piece of information is this 11.7, which represents the length not of an entire segment here, but just part of one. So let's see how that idea relates to theorem 12.3, the ice cream cone theorem. And I tell you what, I'm going to go ahead and label some points here, guys. In the triangle, I'm going to call those points A, B, and C. And the points of tangency, I'm going to call an X and a Y and a Z right over there, just so we know what we're talking about as we go through this. So what we know here is that the measurement of line segment CX, this one right here, is 11.7. So to use the ice cream cone theorem, we want to look for another tangent segment that comes to the same circle from the same exterior point. Well, that exterior point is point C, and the other tangent segment is CY right over here. That segment would have to be congruent to CX. That would need to be 11.7 as well. So now, let me switch colors on you here, guys. I'll go to blue here. Now the question becomes, how long is YB? Well, to figure that out, we know that the entire distance from C to B is 23.5, and 11.7 of that is used up on the left. So we're just going to subtract 23.5 minus the 11.7 that was used up on the left, and that tells us that the other piece here is 11.8. Okay, so the 23.5, the 11.7, this is 11.8. Now that's the length of the tangent segment that goes from B to Y. So going around the horn here from B to Z, going back to the ice cream cone theorem, that would have to be 11.8 as well. And that's half of what we needed to know. Now we're going to start going the opposite direction. Let's take a look at what's going on from A to x, right up here in red. Now again, this whole tangent segment out here, AC, is 23.7, and we've got 11.7 of that used up. So if we subtract 23.7 minus 11.7, that's going to leave us exactly 12 left over for the distance from A to X. And one more time, going to the ice cream cone theorem, AZ would have to be 12 as well. So what I'm hoping we see, these two sides here have to be congruent. Let's take a look. These two sides here would have to be congruent. And go purple here. These two sides here, CX and CY, have to be congruent as well. And now that we know all of that, let's go to green. We haven't done this yet. We know here that the entire distance, everybody, from A to B would have to be the sum of 12 and 11.8. And if we add those two together, not too tough to do in our heads, we're going to get 23.8 for the measure of AB. That's the other side that we needed here in order to figure out the perimeter of this figure. So we should be able to answer this pretty easily now. 23.7. Let's see here, 23.7 added to 23.5 added to, and the side we just came up with was 23.8, and that's going to get us a total perimeter for that figure here of 71 units. Okay, that's our answer there for number 9, and sure enough, that one is correct. Okay, so 10 works kind of the same way. 11, these problems were a little bit weird because, and CUDA worksheets don't do this very often, but they did here. They gave you a little bit of extra information. Let's see what's going on. Directions say to solve for x and assume that lines which appear to be tangent are tangent. So as it looks here, we are allowed to assume that this point here, I'll call this point A, is the center of your circle. It then looks like we've got a line here that's tangent to the circle. So if I called this point B, we know that we've got a tangent line here, let's say from B to C. So there's one tangent. But it looks like there's another one right down here that goes, let's say, from C to D. So we've got two tangents within this problem. Well, the idea at work here in number 11 is, just like it was in number 9 that we just did, the ice cream cone theorem here, theorem 12.3, saying that two tangent segments drawn to the same circle from the same exterior point have to be congruent. That tells us that line segment CB and line segment CD have to be congruent to each other. They have to have the same length. So our equation then is going to be negative 8 plus 2x, that's the measure of CB, has to be equal to the measure of CD, which is x plus 2. And what we can find here, guys, is that this information right here of AD having a length of 7.5 is completely irrelevant in this problem. It doesn't really help us at all. So let's go back to what's going on here. What we would probably do, let's see, I've got a 2x on the left, a 1x on the right, so I would subtract an x from both sides. At the same time, I'd want to move the constants to the right, so I would add an 8 on both the left and the right also. Those terms are going to cancel. Those terms are going to cancel. 2x minus x is just 1x. And on the right side, 2 plus 8 is going to get us 10. That's the value of x, everybody. And all the directions said to do was to solve for x. So we've got it. So as I said, this 7.5 right here really didn't end up being relevant in this problem here at all. Okay, number 12 works in pretty much the same way. And then let's look at 13 through 16. These problems are a little bit weird. Your book doesn't cover any of these, and I didn't put any of them in our notes, but I thought they were useful problems anyway, so I put 4 of them on the worksheet. But let's talk about what's going on here. So the directions here say to find the angle measure that's indicated, and we're going to assume that lines which appear to be tangent are tangent. So we're allowed to assume that this point right here is the center. Again, I'll call that point A. And as I look for tangent lines, the only one that I think I see is this one over here on that side of the figure. So I'm going to call this point B. We'll call this one point C. And just so we get everything else with a name, that'll be D. And this point over here will be E. Okay, and that's where we're at. Kind of the big idea here, guys, is that we've got multiple triangles within this figure. We've got the big triangle that goes from C to B to E and then back to C. So that's one triangle right there. There's another smaller triangle that goes from D to A to E, and that one right there. Now, two important ideas are at work here in both of those triangles. Number one, if we know that line segment CB is tangent to the circle, which they tell us we can assume here, we know that we've got a right angle here in angle CBE. That one has to be 90 degrees. The other important idea, let me go back to the smaller triangle, triangle ADE. That's a triangle that's made up of two radii of the same circle, and we know that all radii within a circle are congruent. So let's take a look at what's going on. Actually, before I get to that, I tell you what, let me go back to the large triangle here, CBE. We now know two angles within that yellow triangle. We've got a 90-degree angle in the bottom left corner and a 54-degree angle up on top. So what I want to do right now, guys, is find the measure of this angle. And the easiest way to do that when you know two angles within a triangle is to take the sum of all three angles, which is always 180, and subtract the two you know, minus the 90-degree angle and minus a 54-degree angle tells us 36 degrees is the measure of our missing angle right here. So that one is 36. Now, back to what I started saying a second ago. Let me get rid of this guy here, everybody. Let's now focus on the smaller triangle, triangle ADE. And what I started to say a moment ago is that that triangle is made up of two radii within the circle. AD is a radius, and so is AE. And all radii within a circle are congruent. That means the triangle ADE is isosceles. And the important thing about an isosceles triangle, in addition to having two congruent sides, it also has two congruent angles. So this angle right here has to be 36 degrees as well, the same as this one right over here, angle AED. Now, back to the issue at hand, everybody. What we're interested in is what's going on in this angle right here. Well, these two angles added together, this unknown and this 36 right here, have to add up to 180 degrees because they make a straight line. And if we know that this angle next to it is 36, we would just take 180 and subtract the 36-degree angle next to it and get a 144-degree angle for the missing measurement, which was located right here. So that's how they came up with that 144. So again, two big ideas right there. Number one, the large outer triangle was a right triangle because we knew we had a tangent line. And number two, the smaller internal triangle was isosceles, which means it had two congruent angles. So 14, 15, and 16 work on a similar concept there. Some of them work in the opposite order. So let's use this example and see if we can't figure out the rest of those. All right, guys, let's try the rest of that 12-1 worksheet. Let me know if you have any questions. Good luck.